there is no building or anything else, it continues a trajectory both forward in time and backward in time. And it says that whatever seconds, 1 second before you set your clock to 0, it would have been in the ground. What it means is, if you release a rock at that location 1 second before with a certain speed that we can calculate, it would have ended up here with precisely the position and velocity it had at the beginning of our experiment. So sometimes the extra solution is very interesting. And you should always listen to the mathematics when you get extra solutions. In fact, when a very famous physicist called Dirac was looking for the energy of a particle in relativistic quantum mechanics, he found the energy of a particle is connected to its momentum. This P is what we call momentum, and its mass by this relation. So particle of mass m and momentum p has this energy. So you solve for the energy, you get two answers. Now your temptation is to keep the first answer because you know energy is not going to be negative. Particle's moving, it's got some energy, and that's it. But the mathematicians told Dirac, you cannot ignore the negative energy solution because it tells you there's a second solution, and you cannot throw them out. And it turns out the second solution with negative energy was when the theory is telling you, hey, there are particles and there are antiparticles. And the negative energy, when properly interpreted, will describe antiparticles. So the equations are very smart. The way the physics works is you find some laws of motion in mathematical form, you put in the initial conditions or whatever, you solve the equations, and the answer that comes, you have no choice. You have to accept the answer. If there are new answers besides the one you were looking for, you've got to think about what they mean. And that's one of the best things about physics, because here's a person who was not looking for antiparticles. He was trying to describe electrons, but the theory said there are two roots in the quadratic equation, and the second root is mathematically as interesting as the first one. It has to be part of the theory, and in trying to adjust it so it can be incorporated, you discovered antiparticles. So always amazing to us how we go into the problem. Our eye or mind can see one class of solutions, but the math will tell you sometimes there are new solutions. And you've got to respect it and understand and interpret the unwanted solutions. And this is a simple example where you can follow what the meaning of the second solution is. It means that to the problem you posed, there is more than the answers that you could imagine. Here it meant particle that was released from the ground earlier. There it meant something much more interesting, namely antiparticles accompanying particles. They are going to accompany particles surely as every quadratic equation has two solutions. All right. So now in this problem, we can do something slightly different. And that's use this expression here, and I will do that, then I'll stop for today. If you were asking questions like, how high does it go? But you don't ask, when does it go to the highest point? Then you don't have to go through the whole process of finding the time at which it turned around. I don't know where that is, that disappeared on the blackboard. Then putting the time equal to 1 second into this formula. If the question of time is not explicitly brought up, then you should know that you have to use this formula. So how do we get it here? Well, we say at the top of the loop, when it goes up and comes down, the velocity is 0. Therefore, you say 0 square equals initial velocity square plus 2 times minus g, that's my acceleration, times y minus y0. If you solve for that, you find y minus y0 equals v0 squared over 2g. And if you put in the v0 I gave you, which was what, 10, that's 100 over 20, which is 5 meters. So y equal to y0 plus 5 meters, and that is the height to which it rises. I think we got it somewhere else. We found the maximum height to be 20 meters. Another thing you can do is you can find the speed here. If you want to find the speed there, you put the equation v squared equals v0 squared plus 2 times minus g what is y minus y0? The final y is 0. The initial y is minus is 15. You solve for that equation, then you will find the final velocity. So if time is not involved, you can do it that way. I want to derive the last result in another way. Then I will stop. And that's pretty interesting because it tells you the use and abuse of calculus. So I'm going to find for you this result using calculus in a different way. So from the calculus, we know dv dt is equal to a. So multiply both sides by v. Now, you have to know from elementary calculus that v times dv dt is really d by dt of v squared over 2. Now, I hope you guys know that much calculus, that when you take a derivative of a function, namely v squared over 2 is a function of v, and v itself is a function of t, then the rule for taking the derivative is first take the v derivative of this object, then take the d by dt of v, which is this one. On the right-hand side, I'm going to write as a dx dt. This much is standard. But now here is what I'm going to do something which somehow we are told never ever to do, which is to just cancel the dt's. You all know that when you do dy dx, you're not supposed to cancel that d. That's actually correct. Okay? You don't want to cancel the d in the derivative. But this happens to be completely legitimate. So I'm going to assume it's true, and I'll maybe take a second to explain why it's legitimate. What this really means is, in a given time delta t, the change in this quantity is a times the change in this quantity. Therefore, you can multiply both sides by the delta t, but the only thing you should understand is delta t, as long as it's small and finite, will lead to some small and finite errors in the formula, because the formula is really the limit in which delta x and delta t both go to 0. So what you have to do is multiply both sides by delta t, but remember it's got to be in the end made vanishingly small. As long as we understand that, we can do this cancellation, and this says on the left-hand side, the change in the quantity v squared over 2 is the change, a times the change in the quantity x. So add up all the changes, or what you mean by integral, same thing, add up all the changes. The change in v squared over 2 will be the final v squared over 2 minus the initial v squared over 2, and the other side will be a times the change in x, x minus x naught. And that's the formula I wrote for you. V squared is v0 squared plus 2a x minus x naught. So the point is, whenever you have derivatives with something over dt, do not hesitate to cancel the dt's and think of them as a delta of v squared over 2 is equal to a times delta of x. This will be actually true as long as both quantities are vanishingly small. They will become more and more true as delta x and delta v squared become vanishingly small. In the limit in which they are approaching 0, the two will be in fact equal. If delta x is a finite amount, like 1 second, this will not be true, because in the starting equation, delta x and delta t and delta v squared were all assumed to be infinitesimal. So don't hesitate to do manipulations of this type, and I will do them quite often. So you've got to understand when it's okay and when it's not okay. What this means is, in a time delta t, if this quantity changes by some amount, and the same time delta t, that quantity changes by some amount, then keeping the delta t equal to some number, we may equate the changes in the two quantities. Provided it is understood that delta v squared over 2 is a change in v squared over 2 in the same time in which the particle moved a distance delta x. Then by adding the differences, we eliminate time and we get this final result. All right, so if you go to your website today, you will find I have assigned some problems, and you should try to do them. They apply to this chapter. Then next week, we'll do more complicated problems that involve motion in higher dimension, how to go to 2 dimensions or 3 dimensions.